Hello.
Hello. Is this working?
Yes, I am traveling, so apologies. I will make you host. Which one should I make the host the one without the camera? Is that correct?
Yes, then I can share screen.
Okay. Okay, yes. So this should be recorded in the cloud. Okay, perfect.
Turn this off so we don't get interruptions.
Just one more thing. If you could send me the notes from the webinar so I can publish them later on.
Okay, yeah, I can do.
Okay, thank you.
You all had a chance to look at the sheet. Has that been published? Sent out?
Yes, the sheet has been.
I'll give it a couple of minutes, I think, just to let people join and then we'll get started. Okay, I think we can probably get started. So so you've all seen the sheet, but I think it'll be nice just to kind of run through the key ideas for each section, just as a reminder, so it's fresh in our heads when we start doing the questions. So the first law of thermodynamics, in many ways, it's just energy conservation. And it's given by a small change in the internal energy of a system. So the standard example is a container full of gas, but it could be anything. So the small change in the internal energy, that is equal to the heat put into the system plus the work done onto the system. So the internal energy, U equals internal energy. This is the energy the material has, or the system has, from its thermal motion. So for a gas, it's from the atoms spinning around and whizzing around and things like that. And we saw last week that for an ideal gas, for a monatomic ideal gas, we have U is 3/2 nRT. So for n moles of an ideal gas with only 1 degree of freedom, this is the internal energy. And you remember this from the equipartition theorem, maybe. Okay, the next part of this first law equation is the work. So, as I said, the last part is the work. And we take dW is work done onto the gas or the system, right? So if you squish it, you're doing work. So if I take a piston or a balloon and I squish it, I'm doing work on the air in the balloon, and so it's gaining energy. If a piston is allowed to expand, then the piston does work on whatever it's expanding into. And so the gas inside the piston would lose energy. So you need to be careful about which way the energy flow is going. But we can rewrite the change in work in a nice way. So let's say we have a piston and it's full of gas. Then there is a pressure on the piston. And this pressure is going to make this bit of the piston expand. And when it does so, it does some work. So we know work is equal to force times distance. So the force on this bit of piston, on this plate here, so we have, that is pressure times area. And then the distance it travels, let's say it just travels a little distance, dx. It's a little distance, so let's make a little dw. So it's a small amount of work being done. So the distance is dx. Now, there's one thing we need to add in, and that is, this is work being done by the gas to expand it. So we need a minus sign in here, because the gas is losing energy as it does this work. And then finally, we see that this here, if the plate moves a tiny bit, then the gas now takes up this blue space. And this volume here, between the blue and the red, this has a volume dV, equals A dx. And so we can rewrite work as minus P dV. So pressure times a little change in volume. Then, finally, you've seen heat before, which is this last bit of the first law equation. And again, we can rewrite this as heat is heat capacity times mass times the change in temperature. And hopefully you remember this equation from last week. Does this all make sense? And so we can rewrite the first law as du equals Cm dt minus P dV. Okay? Does this make sense? Okay. So let's look at the first question, or the 8th question, since we did 7 last week. So something that may have been a bit glossed over is that heat capacity is partly a property of the material. So different gases and different everything has different heat capacities, but also it depends on the way you heat it. So if I have a piston and I heat it, but keep the piston fixed size, that's going to require a different amount of energy. In fact, it's going to require less energy to heat it than if I allow the piston to slide. So just quickly, why do people think that keeping the piston at a fixed volume requires less energy than allowing the plate to slide? Anyone have any ideas? Exactly. So someone in the chat, if it's at a fixed volume, then there's no work being done. So all of that heat you put in goes into changing the temperature. If you allow the piston to slide, then as you heat it, not only does that energy go to warming the gas, but it also goes into doing work. So that's why it requires more energy. So let's show for an ideal gas that how much more energy you need if you allow it to slide. So Cp here means constant pressure. The subscript P means it's a constant pressure, and it's kept at a constant pressure, say, it's just open to the air, and therefore this is the one that's allowed to slide. Cv, on the other hand, is a fixed volume, can't slide. Okay. So we want to compare if we have, so firstly, we're looking at specific heat capacity. So let's just consider 1 kilogram of gas. We want to compare the heat needed to change the temperature by an amount dt. So, as we saw above, the internal energy for an ideal gas just depends on temperature. So, du equals 3/2 nR dt. And because we're looking at the same temperature change, whether or not we're keeping the volume fixed or the pressure fixed, the change in internal energy is going to be the same for both. So we have du P const equals du V constant. Okay, now we want to compare the heats. So we're going to use the first law, but we're going to use it rewritten like this. So when pressure is constant, we have du equals Cp times, well, 1 kilogram. We'll just leave it as m for now, times dt. Then the work done is the pressure, which is a constant, times the change in volume. Now, when V is held constant, we can use the first law again, and heat is given by CV this time, mdt, and then there's no work done because the volume isn't changing. So we want to compare Cp and Cv. So let's divide by dt. We have Cp, m, don't need the dt, we're dividing it out, minus P dV by dt, with P held constant, equals Cv times the mass. Okay. Have you seen partial derivatives before? I think you have, but yes, okay, good. Now, the last step, or nearly the last step, is we want to rewrite this dV by dt. So if we use the ideal gas law, PV equals nRT. So we have V equals nRT over P. And now we want to differentiate this with respect to T, with P being held constant. So this entire thing here is just a constant. So we have dV by dt equals nR over P. If we substitute that in, we get Cp m minus nR equals Cv m. Now, if we look at the final result we wanted to get, we're almost there. All we have is some factors of m to deal with. Now, we're looking at specific heat capacity. So I said we're just going to want 1 kilogram of gas. So we set m equals 1 kilogram, and therefore the number of moles we need is just the number of moles in 1 kilogram. So Cp equals Cv plus n 1 kilogram R. So here we find that it requires more heat to heat a gas if it's at constant pressure, and hence in order to keep the pressure constant, it must be able to expand than if you keep it fixed. And that's because of the extra work needed. Does that make sense to people? Are there any questions about this? Okay. Now, there's one thing I wanted to make here as a little aside, since we kind of saw it halfway through, and it's going to become useful later. So we saw du equals CVM dt, let's say C at the moment, minus P dV. Now, if things are held constant, so if volume is held constant, then this term is 0, and this here is CV. So du is CV m dt. And this is always true. This is true even if the process isn't held constant. The change in internal energy is always CV times the change in temperature. But that's always true, even if the volume isn't fixed. But it's the right-hand side that then has different terms to compensate. Does that make sense? This relationship will be important in later questions. Okay. Let's look at the next problem. So we have 100 ml of water, and this is heated and turned into steam at 100 degrees Celsius. And then it's just kept at 100 degrees Celsius. There's the top of this piston here, the top of this container can slide. So it's kept at atmospheric pressure. So this is a constant pressure process, but volume is allowed to change. The question is, how much work is done by the steam? And we haven't discussed phase changes on how much energy you need or how much heat you need in order to boil something. That doesn't matter. We're just looking at the work done. The question isn't asking how much energy does it take to boil. The only thing we're looking at, we're going to need to worry about, is the change in volume. And essentially, compared to the steam afterwards, the initial volume of water is negligible. Gases take up so much more space than liquids and solids. So 100 ml of water equals 100 grams of water, which there's 18 nucleons in a water molecule, 2 hydrogen atoms, which each have 1, and oxygen has 8 protons, 8 neutrons. So this gives us 5.6 moles of water. Okay, so now we need to look at volume after boiling. So we have the volume is equal to, and we're just going to treat it like an ideal gas, nRT over P, which we've seen before. And now we need to put numbers in. So the temperature, remember, every time we use the ideal gas law, we need to use temperature in Kelvin. So we have temperature equals, well, it's 100 degrees Celsius. And remember, you have to add 273. So that's 373 Kelvin. And pressure is atmospheric pressure So that's 10 to the 5 pascals. So this is equal to, well, N is 5.6, R, which was 8.31. The temperature is 373, and then divided by 10 to the 5. Then I got 0.17 meter cubed. I should have units here as well. Okay, so this is the final volume of this water after it's been boiled away into steam. Okay. Now the work done. dW equals PdV. All right, and because we're looking at work done out, this is positive. Pressure is a constant. So if we were to integrate this, we'd have work done is equal to P times the change in volume, which is equal to 10 to the 5 pascals times 0.17 meter cubed, which is equal to 17 kilojoules. There's a lot of energy to heat this. A lot of work has been done by this steam engine. Take even more energy to heat it. Takes a lot of energy for water to boil and change temperature. Are there any questions about the first law or any of these problems? By constant pressure. So the pressure in the, so if I were to take a balloon, say, you may have seen this, or I think it's often the experiment you do in secondary school is like year 7 or 8 is with a can. But say if you have a balloon and you were to heat it, then the gas inside gets faster and so it increases in pressure. Now, if it's a balloon with a rubber surface and it's in the air, if that pressure inside is greater than air pressure, then the balloon is allowed to expand until the pressure inside the balloon is the same as the pressure outside the balloon. And so constant pressure means there's usually something outside, like the atmosphere, that if the pressure gets too high, something can slide until the forces equalize. So with this example here, again, there's the atmosphere on top. So as you heat it, the top's allowed to slide. Because if the pressure in the gas is higher than the pressure in the atmosphere, there'll be a force upwards. So it slides up. So that's what I mean by constant pressure. It means the pressure is kept constant, and usually that's because something can slide to equalize forces. Okay, so the next section is thermodynamic processes. So the things we've looked at maybe been quite simple changes. We're going to see things where the pressure and volume are varying in maybe more intricate ways. So let's have a look what these look like. on a diagram, one of these diagrams. This is called a PV diagram, and it just tells you how pressure and volume are related as something happens to the gas or to the system. And then because of the ideal gas law, you can use this to calculate temperature. So what does anyone remember what? So they all have fancy names. So does anyone know what an isochoric process is? I'll pull the other diagrams while waiting. Constant volume. Yes. So an isochoric process is this. Now, what about an isobaric process? Constant pressure, yes. And then isothermic, or isothermal. Constant temperature. And this looks like a curve like this. And the reason is pressure equals nRT times 1 over V. So this here is just a constant. We just have pressure is proportional to 1 over volume. That's why you get this curve. Okay. Now, another type of process that comes up all the time is an adiabatic process. And this is one where there is no heat exchanged at all. Now, this is quite common in an engine. So if something is well insulated, or if a piston moves quite quickly, and so quickly that there hasn't been time for heat to escape, then things are approximately adiabatic. So there's no heat transfer, and any change in the internal energy is equal to the work done. So, and quite a common mistake is people think, because there's no heat, that when I've been teaching this class in their third years, lots of people think that there's no heat exchanged, and therefore temperature is constant. But that's not true. Temperature can still change. T varies. Okay. And it changes because you have to do work. If you if you push a piston really fast, it's going to be pushed together and it's going to heat up. Okay. And we see that there's a complicated law between the start pressure and the end pressure. And we're going to use that law later in other questions. And I think it's similar to one you've worked on your sheet, but I've used different quantities slightly. So that for an adiabatic process, we have this relationship between the volumes and the temperatures. So, I mean, this is a week that started with the first law, so maybe that's a good place to start. du equals dq plus dw. It's an adiabatic process, so this goes to 0. So we can rewrite this as CV dt. Remember, we said that the internal energy is always given by CV dt, even when the volume isn't constant. And this is equal to minus P dV. Okay, if we now look at we now use the ideal gas law, we have minus nRT over V dV. Now, if we rearrange this, have you seen differential equations and things? Do you know how to solve things like this? Have you seen this equation or type of thing before? Yes. Okay, this isn't completely new. Okay, so we have dV dt over t equals minus nR dV over V. So to solve this differential equation, let's integrate both sides from point A to point B. Has people seen what is the integral of dx over x? Have people seen this integral before? Does anyone know what it is? Ln x. Yes, good. Okay, you have all seen this. Ln x. And so we do this integral. And we have CV ln TB over TA equals minus NR ln VB over VA. Now, what is minus ln of x equal to? Have people seen this? People remember? Ln of 1 over x. Okay, everyone's up on their log rules and things. Okay. So that means we can write this as NR ln VA over VB. Let's find ourselves with the final result. Okay, so we just want, looking at this, we just want the V's on one side and then everything else on the other. So let's rewrite this. Ln VA over VB is equal to CV over NR ln TB over TA. And we've seen that you all seem to be happy with your log rule, so I'm not going to ask you. This becomes ln of TB over TA to the power of CV over NR. Okay, does anyone know of what do you think the final step would be? We're almost there. What's the final step to get rid of these logs? Yes, you take e to the both sides. E to the power ln A is just equal to A. So if you do this to both sides, we get rid of the logs. We have VA over VB is equal to TB over TA to the power CV over NR. Okay. People happy? If you understand this, this is kind of something you do kind of maybe in your second or third year of university, this kind of question. So you can do it already. Does this make sense? Excellent. There may be a fair bit of maths, but it is hope, or it was, Maths, you understood. So that's good. Didn't have to recap on anything there. Okay. So now we have two different processes. So a gas can go from point A to point B here, either by doing an isothermal process, so the pressure and volume are changed in such a way that the temperature is held constant at all times. Alternatively, we can cool the gas, we can expand the gas, keeping the pressure constant, which means we have to heat it up, and then we let it cool down at constant volume. So we'll see that once we get from the start to the end, then the internal energy is the same no matter which way you go. And this is really important. So things like work and heat depend on the way, depends on what you do, depends on how you heat the gas, how it expands, how the pressure changes. But the overall energy that's in the gas, the end, doesn't depend on how you got there. It just depends on the temperature. That's quite an important point. So I'm going to say QW depend on path, U does not. And that's what we're going to see in this question. Okay. So let's look at the first bit first. So the gas doubles in volume. How do we show that the pressure here is half the pressure at the start? Which gas law do we, or which equation do we use? Yes, ideal gas law. So we have PV equals nRT, and we want pressure. So we have pressure equals nRT over V. So these three things here, these are just a constant. So we'll just call them C. So let's have a look. So we have P1 equals nRT over V1. P2 equals nRT over V2. But V2 is twice V1. That's nRT over 2 V1, which is equal to a half times the first pressure. Now we do a similar thing to work out the temperature of the corner. C here stands for corner, not cold. The C stands for corner. So let's see. We kind of do the exact same thing. We use T equals PV over NR. Now at point A, we have T equals P1 V1 over NR. Then at the corner, what do we have? We have the volume has doubled, but the pressure stayed the same. So we have the corner is equal to P1 V2 over NR, which is equal to 2 P1 V1 over NR. It's equal to 2 times that first temperature. Okay, so the temperature at this corner has doubled. is double what it started as, which kind of makes sense. Pressure stayed the same and the volume has doubled. So the temperature's doubled too. Okay, what was the next part? Show that the change in internal energy is the same for the red and the blue processes. So for the red, well, it's an isothermal process. So does anyone know what the change of internal energy is for an isothermal process? What's the change in internal? It's zero, exactly. And that's because for an ideal gas, the internal energy is just a function of temperature. So along an isothermal process, the internal energy isn't changing. Any work done is cancelled by any heat in. Now, the blue process, we're going to have to split it up into two bits. There's the isobaric bit and the isochoric bit. So let's look firstly at the isobaric. So the heat, what would the heat be? What equation would we use? Did I say anything about the amount? No. What would the heat, what equation would I use for the heat? MC dt. We need to integrate it because it's a longer process, but yes, MC dt. Which C do we use? Which heat capacity do we need? CP, because isobaric, exactly. So we do this, and we have MCP 2T minus to the end temperature minus the start temperature, just in the end, MCP T. Okay, that's the iso. Oh, we also have the work to calculate. So the work done. Does anyone remember what the work done is? Remember, we want work done onto the gas, onto the system. So how do we get the work done? Minus PDV, yes. Now, pressure is constant, just the constant P1. So we do this integral and we have minus P1, V2 minus V1, but that's 2V1 minus V1, which is equal to minus P1 V1. Ooh, the 1 went down with it there. Now, what about the isochoric bit? So that's the constant volume bit here. What is the work done in this case? Zero, exactly. Okay, and the heat, which again it's going to be mc dt, but which C? Is it constant pressure or constant volume? CV, exactly. So we do this, and it's mcv, and now we want the initial, so the final temperature, which is T, minus the start temperature, which is 2T. So actually we lose heat in this case. We have minus mcvp. Now finally we want to add all these up. So delta U equals Q plus W, which is equal to Cp m dt, sorry, Cpm T minus Cv m T minus P1 V1. Now this, you may remember from, where is it? Which question was it? That's right, the first one we did today. This relationship between Cp minus Cv. So this is equal to Nr, where, so beforehand in question 8, to the first question we did today, this was N 1 kilogram. It's now just N because it's the total number of moles because we've included the mass. So I'll write that to the side. N equals M times N 1 kilogram. So that's why it's Nr. Minus, under T, P1, V1. Why do people think this is 0? What makes this cancel? Right, we've seen that it must cancel. But why? What law or equation can you use to make this cancel? PV equals nRT. Exactly. We've got nRT minus PV. Exactly. Are there any questions about this? These are not short or easy questions, so. Is there anything you want me to go over quickly before we move on? Okay. Finally, this is a long question. This is the kind of question you would definitely get in a university exam. So, oh, I forgot to go through what we need to understand first. Whoops. Okay, so the kind of engines we're going to be looking at is called a heat engine. And these work by, if you have something that's really hot and something that's really cold, then heat flows from the hot thing to the cold thing. And you can use this flow of energy to power an engine. So heat flows in, we can take some work out, and then some heat flows out to the cold thing. And we can use this work to power some kind of engine. And the efficiency of one of these engines is the work out divided by the heat in. Now, by energy conservation, work out is the heat in minus the heat out. Which is equal to 1 minus Q out over Q in. So we see that unless it's 100% efficient, there's always going to be some heat flowing to the bottom, flowing to the cold thing. And yeah, these kinds of engines, thermodynamics was really big in kind of Victorian England, Victorian Britain rather. And so they loved these kind of engines. They would give an understanding of what could be done with engines, with steam engines, you know, and that was really important for the Industrial Revolution. So this is historically a very important topic, as well as an important one for physics. Okay. All right, so we have an engine that has 3 stages. So these engines always have multiple stages of something heats up, compresses, cools down, whatever goes on. They can be quite complicated. This one only has 3 processes. So the first thing is it expands isothermically, then it cools down, and so depressure, and so the pressure decreases, and then it contracts adiabatically, and so it might heat up, or will heat up in this last process. So we want to calculate the work done and the heat put into the system. So let's have a look. The heat is going to enter here from the hot thing, from the hot object. Now, this second process here is where the heat is going to leave. And this adiabatic thing here, there's no heat, so we don't worry about it. So let's look at the work done and heat in each of the 3 processes. So A, for the isothermal expansion. So we know that du equals 0. So how do the heat and the work relate for an isothermal expansion? So something's isothermal, there's no change in internal energy. So how do the heat and work relate to each other? All heat goes to work. So yes, Q equals W. So this means once we work out one, we can work out the other. That makes life easy for us. Okay. This isn't a constant volume or a constant pressure process. And we can't really use that heat equals Cm dt. So we're going to have to use work. So the work done is integral of P dV, which is equal to integral of N RT over V dV, where this temperature is the constant hot temperature, TH. And this, if we integrate, well, we can pull out these constants first. Integral dV over V. And people said what this integral was on the chat earlier. It's log V, ln V. So we have nRTH ln of V2 over V1. Oh, whoops. And that is equal to the heat. Okay. Let's look at the second process. This is a process at constant volume. So what's the work done in this process? Zero, right? So that's P dV, but V doesn't change. So there's no work done. And so, how do we get Q? Change in internal energy. Yes, they are equal. But how would we get change in internal energy if we wanted to go that way? Exactly. dVm dt. Okay, we integrate that because it's changing. And so the temperature changes Tc minus Th. And we see that this is less than 0, so that heat is indeed leaving the system. This is as we expected. Finally, we have an adiabatic process. And so what defines an adiabatic process? No heat transfer. Exactly. So Q equals 0. And so du equals work. Now, we have to put a minus sign here. The reason is we were looking at work done by the engines. We want to look at work that leaves. Getting these signs right is really tricky. You know, be very, very careful every step of the way, always thinking about which direction the energy flows. We want the work that leaves the engine. And so the change of the energy of the engine is going to decrease as it does work. That's why we need the minus sign. Now, what did we say earlier is a nice expression for du? Anyone have it written down, or do they remember? Yes, exactly. du is CV dt. I'm keeping the m's in there just to be precise. And then we have, so we do the integral, so the total change in internal energy, we integrate this, and we have delta U is equal to minus the work done is equal to CV TH minus TC. Okay. Now we want to work out the efficiency. The last bit of the question is the efficiency, and we can write this in terms of TH and TC. Now, for those of you who have got this far in the sheet, the Carnot cycle has a really nice result, efficiency in terms of temperature. This engine doesn't. It's going to be not the nicest expression. So the efficiency is work out divided by Q in. So the heat in, well, the heat in only comes from part A. We only have this heat because the heat from part B is leaving the system. So we have nRTH ln V2 over V1. And the work out, so there's work out from part A, which is equal to this. And then we have work from part C. And there. Okay, well, the first term here just becomes a 1. What can we do with this ln of V2 over V1? Okay, I'll give you a clue. V2 and V1 are connected by an adiabatic process. So what do they think they can do? Any formulas we've seen today? If I keep scrolling up, maybe we can see something. Oh, wait, this is about an adiabatic process. So we can, and it relates volume and temperature. It's exactly what we need. And in fact, we already have the logarithm of the volume. So we can use that. Okay. So we have, remember this formula? Yeah, okay, someone's written it. So we have CV over NR log of, which way round is it? T1 over T2 equals log V2 over V1. Now something, and I don't think it's entirely written down, where is it? I think there's a bit of a typo. This should be for 1 kilogram. Here, because this is the specific heat capacity of the gas. So this should have all been for 1 kilogram, that question. So this should, all right, 1 kilogram again. Okay, so let's plug this in. Efficiency equals 1 minus CV MTH over TC over NRTH CV over N1 kilogram. Oh, learn. What was T1 and what was T2? Which way round was it? Let's have a look. So it ends at TH and starts at TC. So T2, TH. So alternatively, we can see that V2 is the bigger volume, so it needs to be the bigger temperature in order to keep the signs right. Oops, there we are. So now a load of things cancel. The CV cancels with this CV, this R cancels with this R. We have N over N1 kg equals M, so they all cancel, this with this and this. And overall we have 1 minus, have I solved it nicely? 1 minus TH minus TC over TH ln TH over TC. Nowhere near as nice as the Carnot cycle, but there we go. Does this make sense? This is all maybe quite involved, but hopefully, since you've had time to look at the sheet and look at similar problems, this kind of makes sense. Okay, then the final question is maybe something you haven't, it's a bit different from the sheet, maybe something you haven't seen before. So these heat engines, so rather than having heat flow from a hot object to a cold object and capturing this energy and making work, instead, we can run these in reverse. So we can put work in, like via electricity or something, and what it can do is it sucks up heat from the cold object and puts out heat to the hot object. So this is kind of how a fridge works. Something that's got quite a lot of attention recently is heat pumps. So these are really good as either air conditioning or room heating. They can be more efficient than 100%, as we'll see. Okay. What we're going to assume, and I'm assuming you've seen the Carnot cycle. So we're going to assume this engine runs on the Carnot cycle because it has this nice efficiency here. A nice simple one. Okay, so if we use this as a fridge, so in other words, for a fridge, what we care about the heat we can suck in from the cold. Right? Fridges are much colder than the outside. So what matters for your fridge is how much heat can you extract from the fridge, from the cabinet with the food in. So if you were worried about the efficiency of a fridge, how would you define that? Right, what's the useful energy and what's the energy you put in to make it work? So what's the useful energy that we care about? Out of these three energies here, do we care about Q in, Q out, or work in? Heat in. Work in is the energy in. And the useful energy is Q in. Now, we can compare this to the Carnot efficiency, and we can use that to see if we can get it more or less than 100%. So we can rewrite this as Q out minus W over W, which is equal to Q out what is this equal to? In fact, it might be slightly clearer if rather than writing Q out, because the heat out goes to the hot end, it says QH over W. So does anyone recognize this? Maybe if I go up slowly. Does anyone recognize it? Yes, okay, 1 over the Carnot efficiency. And then we can sub in for the Carnot efficiency. And after several lines of algebra, this gets TC over TH minus TC. Okay. What is the maximum efficiency this fridge can have? So the Carnot efficiency can be a maximum of 1, but what is the maximum efficiency this fridge can have? Give you a clue. What happens as the cold end gets closer and closer to the hot? So as TC gets closer and closer to TH, what happens? It becomes infinite, right? You can actually extract loads of energy as the temperatures get closer and closer together. If you think about it, if there's a huge temperature difference, it's really difficult to make heat flow from cold to hot. But if they're the same temperature, then heat is just going to flow between them, back and forth, back and forth, back and forth, without you having to do any work at all. And then, yeah, so the efficiency in that case would be infinite. Okay. Okay, so if we wanted instead to use this as a heater rather than a fridge, as a heater, what is the useful energy that we care about? Q out, exactly. Because Q out goes into the hot. And now, what is this equal to? Yeah, exactly, the Carnot efficiency, or 1 over the Carnot efficiency. Which we can then solve to get TH over TC. So, again, what is the maximum efficiency a heat pump heater can have? Infinite again. So this can be greater than 1. So this is why heat pumps are so useful. Okay, now there is a last bit of this question, but it's very much beyond the scope of everything we've done so far, and it was an extension question. And we don't have that much time left, so it might be more useful instead. Are there any questions from the rest of the sheet, from any of the previous questions before, from last sheet, kind of anything about thermodynamics you want to ask? We don't necessarily have time to do that last bit justice, but it's really was a challenge at the end. I'll go back through. So something might jog your memory, something that you thought was confusing. That's fine. I've got this. I'll write up the solution so it will be published eventually if people do want to have a look. But yeah, I don't think we necessarily have time to go through it and do it justice in the next kind of by the end of the class. But I think you've all done very well. This is content that people don't see until kind of halfway through a degree. So the fact that you've been able to do this is very impressive. Okay, how is the work in converted into cooling in a fridge? You're right. So it depends, right? There's loads of different cycles that can do it. I'll go through. So you remember the Carnot cycle. So this has isotherm, isotherm, and then the 2 adiabats. So normally what happens is you start here. So this is if it's running as an engine and we get work out. Instead, if it's running as a fridge, everything goes in the opposite direction. Finish the diagram. So what happens is, so you start here, right? So you have a piston in the back of the fridge that can go up and down. So what they do is you get it to the piston is the same temperature as the fridge. And then you expand it, keeping it at the same temperature as the fridge. And this expansion is what sucks the heat out of the fridge. Then it's kind of disconnected from the fridge and it's connected to the outside air. It's allowed to warm up, or it's pressurized, or depending on the process, it's now at the same temperature as the air. And then you compress it and the heat leaves. Then you connect it to the fridge again and you make it so it's the same temperature as the fridge, you expand it, and that sucks the heat in. And then you make it the same temperature as the outside air, and then you compress it and it pushes the heat out. It works. You can use a Carnot cycle to do it. Okay. Are there any other questions? I mean, if there's no more questions, I don't know if we need to wait for Vlad to come back. He's traveling, so I don't know if he'll be coming back to the call. So in which case, I think you've all done very well. Keep up with this and understand this and follow through these questions. And I think well done. And I don't know if I'll be doing another one soon at any point, but if not, goodbye. If I do, please see you soon. And I think we can end the call here.